I want to calculate the length along this parabola from x equals 0 to x equals a. It's just the parabola y equals x squared. It's not that interesting to calculate this length. I mean, maybe it is interesting in the sense that you don't know how to calculate lengths of very complicated things in general, and this could give you a nice way to calculate the length along something other than a straight line or like a piece of a circle. But what's more interesting about this is that this family of integrals comes up in all kinds of applications, applications that you wouldn't expect. So there are physical applications where you're calculating work or surface area or mass. There are other times when this kind of integral can come up that you wouldn't expect. So it's very nice to be able to handle something like this. This calculation is a little long, so I'm going to go through it quick, but it uses the method of trig substitution. And so basically what I'm going to do is replace 1 plus 4x squared with a trig expression that will simplify the square root, get rid of it. I'm going to use the equation 1 plus tangent squared equals secant squared. So I want 4x squared to be equal to tangent squared. That means I want tangent to be equal to 2x. By the way, the expression inside of here is coming from the formula square root of 1 plus f prime of x squared, where f prime of x is 2x. I want to get dx in terms of d theta, because this is going to become the integral of the square root of 1 plus tangent squared, so the square root of secant squared, which is secant. But I'm not sure about the dx here. So I'll divide both sides by 2 and then calculate dx d theta. So now dx d theta is 1/2 secant squared. I'll solve for dx by multiplying both sides by d theta and then just plug it directly in. Bring the 1/2 out. To handle secant cubed, you want to rewrite it as secant times secant squared and then use the reverse of the product rule. So use integration by parts to try to finish that up. I will calculate the integral of secant cubed off to the side. If you happen to have this memorized, that's great. You can just plug it in from here and then just rewrite everything in terms of x instead of theta, and then plug in your bounds. All right. I'm going to use the product rule, the integration by parts. I know I can find an antiderivative for secant squared, and I can find a derivative for secant. So I'm going to choose f equals secant, and g prime equals secant squared, and f prime is secant tangent. The antiderivative here is tangent. So integration by parts tells me I get f times g minus the integral of f prime g I'll need these formulas that I just erased later, but I'll come back to them and write them down again. All right. It looks like I've got something just as complicated now, but remember I can replace tangent squared with, I guess I just had the formula written down. It was 1 plus tangent squared equals secant squared. So if you solve for tangent squared in that equation, I'll just write it out like it was. If I solve for tangent squared, I get secant squared minus 1 by bringing that over here. So plug that in for tangent squared and distribute. When I multiply this out, I get a secant cube term, and then I'll get a minus secant term. I'll split that up into two different integrals. So first I've got the integral minus the integral of secant cubed. And then the two negatives cancel out. I get a plus integral of secant. The integral of secant is something that I'm going to assume that you've already learned. If you haven't, there's a way to manipulate this algebraically and then use a u substitution to get to that antiderivative. Assuming that you know how to do this, what we can do from here is now add this term to both sides of the equation. So it will go away from this side. And on this side, when you add the integral of secant cubed to the integral of secant cubed, you get two copies of that. So on the left, we got 2 integral of secant cubed. On the right, we got secant theta tangent theta plus that integral. Divide both sides by 2. This is, what is that? Natural log of secant theta plus tangent theta, absolute values. I'm going to have bounds on this. My bounds go from x equals 0 to x equals a. I'm just going to keep them in terms of x for now. So over here, I'll be evaluating at x equals 0 and x equals a. Notice what I actually need in this problem is 1/2 of the integral of secant cubed. So I'll have to multiply this times 1/2 to get 1/4. So the length that I'm looking for is 1/2 of that, so 1/4 times, and then I need to plug in x equals a into this and x equals 0 into that. I want to go back and rewrite it all in terms of x before I try to plug in those x bounds. So if you remember, we chose tangent theta to be equal to 2x at the beginning. So I'm going to be able to plug in 2x for tangent theta. And then the reason we chose that was so that the square root of 1 plus 4x squared would turn into something where the square root goes away. So we had the square root of 1 plus tangent squared gave us the square root of secant squared, which was just secant. So that original square root of 1 plus 4x squared is exactly what turned into secant. If you don't believe me, just go back and look at the beginning. Pretty sure that's what it was. I don't have quite enough room, so I'm going to write it down here. just plugging in for secant and tangent in both terms there. All right, now I have this 1/4 out in front. I need to plug in x equals a and then do minus, plug in x equals 0. When I plug in x equals 0, sometimes all the terms go away, so let's see if that happens here. X equals 0 into this term gives me 0 times some stuff, so that will go away. And then here I'll have the natural log of the square root of 1 plus 0. That gives me the natural log of 1, and the natural log of 1 is 0. So when I plug in 0, everything goes away. I'm just going to plug in a and write that down. Now, I'll write the 2a in front of the square root. I don't actually need absolute values here. It's fine to keep them, but a is a positive value. So I'm just plugging a into here. There's my final answer. This is surprisingly complex, I think, when you think about what we're calculating, which is just this length from x equals 0 to x equals a. But at the same time, you've never been able to calculate the length of that thing before. So maybe it's not too surprising that it's more complex than something like the length along the edge of a circle. And remember, the importance of this is that this handles much more interesting applications than just the length along a parabola. So for now, you just have to trust that it shows up and try to learn the method. It would probably be good if I or someone made a video trying to convince you of all of the important places that it shows up, but I don't have that on the top of my head.